Oh, wait, they can't. Okay, here we go. Okay, so here, so this is chapter 12, which is actually, again, the last chapter in the book, I think. Was the last one we're going to cover in this course anyway. So if you remember what a distribution is, you know, there's lots of variables that we do work with in statistics. You know, there's variables for test scores. You know, if you have a population in your class, that is, and you want to analyze, you know, the test scores on an exam, the variable would be the test scores. Or for instance, if you could be studying the body weight for a group of body weights for a group of people, you know, that would be your variable. With a variable, we like to consider what's called its distribution. Okay? The distribution of a variable, by definition, it's all the possible values the variable can take on. In other words, it's its range, you know, if you think of it as a function. Also, also the frequency each possible value can actually occur. Also the frequency that each possible value can actually occur, of each value that can occur. Okay. Okay. So that's what happens here with the, what do you call it, with the distribution. Let me see if I can, there it is, good. That's what I was looking for, okay? All right, that's what distribution is, and you can actually represent it using frequency tables and histograms, okay? You can represent it using frequency tables, you know, and histograms. We did see that already, right? You know, we saw that frequency, they can give you the values of the variable, right? Like test scores. It can also give you the frequency with which each value can occur. Now, let me just show you something from the textbook. That's what I was looking for. I should have had it open before I started class. I apologize for that. Let me just share it here. What I'm trying to show here with this picture, if it shows up, come on, there it goes. Here, what this is saying is using a curve like this, what you can actually do is you can imagine with the curve estimating the values the variable can take on and their frequencies as well. You know, with a curve, you can do that. It's almost like what the curve is doing is it's touching the top of each histogram bar. So in other words, you can actually use a smooth curve like this to estimate a variable's distribution. You know, to approximate it, in other words. So you can use a histogram, but some people, what they like to do is they like to use a smooth curve instead. You know, it's only going to be an approximation, and that's okay though, right? I mean, roughly you can get the variables, the values of the variables and the frequency. Okay, let me go back to the notes. You know, we have seen that before, okay? Good. Right? You know, that's what I'm saying here. You can imagine that the curve is touching the top of each bar in the histogram. Okay? That's what I'm saying here. And also with a smooth curve, well, such a curve can sometimes be given by a formula. Thus, you can also estimate a distribution using a formula. And now there is a distribution that many variables fit, so to say. You know, like body weight, IQ scores, a lot of those tend to fit a certain distribution called the normal distribution. It's actually one of the most important distributions, the normal distribution. We're going to see what that is in this chapter. We're going to see what that is. We're going to learn about something called the empirical rule. You'll see what that is. That has to do with where the data lies in the normal distribution. Most of it actually lies near the mean. You'll see what I mean, though. There's something called z-scores, and we'll see a special kind of distribution called the standard normal distribution. That's the one that people mostly deal with. I mean, there's lots of different normal distributions, so to say. You actually obtain one for each mean and each possible standard deviation. The standard normal distribution is what people mostly work with. And it turns out that's really enough to work with. And then we can use the z-scores to determine percentage of the percentage of observations within a specific location for a normally distributed variable. You'll see how we're going to use the z-scores. We will use that, okay? You'll basically see between what values are most of the scores, between what values and stuff. You'll see what I mean. The z-scores have to do with going from the normal distribution to the standard normal distribution. But this is what the normal distribution looks like. If you had a distribution with the histogram and you imagine drawing a smooth curve, like we just said, right? If the curve looks something like this, you get a normal distribution. Okay. Notice it's symmetric about this line in the middle. It's symmetric, and it's also bell-shaped. Okay, it's also bell-shaped. But this is what the normal distribution kind of looks like. What actually happens is normally the vertical line that goes through that it's symmetric about, that's actually where the mean is. The average. See, the distribution is symmetric about the mean. So for this normal distribution, it's symmetric, as you can see, okay? It's symmetric about the mean, which in this case is 0. And what's nice about this distribution is the mean, the mode, and the median all equal each other. The mean, the mode, and the median, they all equal each other. Okay? So in this case, for this normal distribution, the mean is 0, the mode is 0, and the median is 0. What's also nice is about 50% of the data values are below the mean and 50% are above the mean. So roughly half and half, so to say. I mean, you kind of would expect that because it's symmetric about the mean. And also you can probably see from the graph here that the further away you get from the mean, the more rare the data values become. Okay? The more rare the data values become. Also, you can see here that the graph, the curve, as you go further and further away from the mean in either direction, right? The curve, the tails of the normal distribution, that is, they get closer to the x-axis, but it never actually reaches it. It gets closer to the x-axis, but again, it never gets there, though. I mean, this might be a little beyond the scope of the course, but we say the x-axis is an asymptote. If you've taken pre-calc or something like that, you would know what that word means. If you don't, that's okay. I'm not going to test you on it. But that's what's happening here, though. And what's interesting with normal distributions is almost all of the area under this normal curve, and the area under the curve does have relevance here. You'll see later on when we get to z-scores, but most of the area is within 3 standard deviations of the mean. Most of the data is within 3 standard deviations of the mean. There is data beyond that, but it's rare. It's not as, it doesn't have as high a frequency, that's bad, right? But this is what the normal distribution looks like. It looks something like this. Okay? Now, what can happen though is, data may not be exactly normally distributed. right? But it can be approximately. I mean, with any distribution, you can have that. You can have a variable whose data doesn't fit the distribution exactly, only approximately. But that's okay. And I also said you can actually use a curve to approximate the distribution of the variable, right? Well, with a curve, you can get a formula usually. In other words, this graph here, this curve, which gives us the distribution of the data, this curve is actually given by a formula. This is the formula. And no, you're not going to have to work with this in this class. Don't worry. I know this is kind of nasty looking. It's not as bad as it looks, though, actually. This exp is actually e to the x. There is a button on your calculator for e to the x. exp, though, is just shorthand notation for this. It's actually what they call an exponential function. Here, b is actually the mean. A is the standard deviation. Okay, so let me say it again. You can use a histogram or a frequency table to present the distribution of a variable, or you can use a smooth curve like this. This smooth curve would approximate the height of those bars in the histogram, okay? And if you have a smooth curve, sometimes you can use a formula. For instance, we can use this formula to graph a normal distribution curve. And the formula does look kind of nasty. Again, it's not terrible, though. And I should say this, the book, I think, does this. You'll see in a second why I did B and A here. But generally for the mean, people use this Greek letter. It's pronounced mu. That's what people use for the mean, this Greek letter. For the standard deviation, people use this. It looks like an O, but it has a tail on top. And this is called sigma for the standard deviation. Okay, let me actually go to this site Desmos. I'm going to show you actually what happens if B and A changes. So it's something in Desmos we're going to use. So let me just click on this. So it should be up. There it comes. Okay, let me just stop sharing this and get to Desmos. There it is. Okay. Not sure if people have access to it, but that's okay. Okay. All right. So this is actually the normal distribution curve, okay? But here you can see the mean, which is again A. This is 1. A is 1. That's the standard deviation. My mistake. B is the mean. So in this case, the mean is 0. Now watch what happens if I change the mean. You can see that the graph is shifting, right? If we increase the mean. Okay. Well. Okay. There we go. See? Well, remember, it's centered at the mean. It's symmetric about the mean. Okay? So in other words, if you imagine drawing a vertical line through x equals the mean, the graph will be symmetric about that line. Okay, so that's what happens when the mean, that's what happens when you change the mean. Now, what about the standard deviation, which is A? Watch this. Here I'm increasing it, see? Standard deviation has to be positive. We're making it bigger. You could see the graph is getting flatter, right? Let me zoom out a bit. Here's what we started with, see? The peak, right? The top is getting flatter. The graph is getting flatter when I increase the standard deviation. Okay? Again, that makes sense. The data is more spread out. When I make it smaller, closer to 0, so this is what we started with. When I make it smaller, you could see that the peak gets bigger. This is just what happens when you change the mean and standard deviation. I thought it'd be good to show that. The link is in the notes, okay? As you can see. All right. So let me now just, okay, so let me get back to the notes.